Okay, welcome back to this next recording, and we'll do some problems related to the first two sections in the diode chapter, uh, ideal diode and terminal characteristics of junction diodes. Those are the first two sections. So you remember seeing this ideal diode slide where I talked about how the external circuit must be carefully designed so as not to damage the diode. So after this, I'm on slide 5. I have a problem from the back of the chapter that we will look at together. So there are a lot of these kind of examples in the textbook, so I just picked a couple. It's not the most difficult, but it does need some basic core ideas that you have to become familiar with. So let's see what the question is. So for the circuit shown in the figure, using ideal diodes, so all these diodes both in part A and part B are ideal. Find the values of the labeled voltages and currents. Okay, so find the V and the I in each case. So before we go to solve this, and you may think this is pretty easy, I can tell exactly what is, I'm going to caution you that it can be slightly tricky. So here are some rules to follow when you're given a situation like this. Which diode is on, which diode is off? That's what we need to find. Okay. So the rules to follow are, at any point in a circuit, only one voltage can exist, right? You cannot have a point in a circuit that has plus 5 volts and plus 6 volts, or plus 8 volts and minus 2 volts, right? At any point, there can only be one voltage. Now this is obvious, it's very simple, you should know it by now, but sometimes we miss the importance of it. So that's one thing to remember. Point 2, if a diode is conducting because it is forward biased, the voltage at anode and cathode are identical. Remember, for an ideal diode, we say that there is no voltage drop that means the resistance is 0 when it is conducting and it's forward biased. So the voltage on both sides, the anode and the cathode, should be exactly the same. Okay, so that's number 2. Number 3, if a diode is cut off because it is reverse bias, then that rule obviously doesn't apply, right? The rule that applies so strictly for a diode that's on, that's conducting, is quite the opposite when it's reverse biased, because it doesn't matter in theory, right? It doesn't matter how big the difference across the reverse bias is, the diode still won't care, right? I mean, it may break down, but in generally it won't care. So the point is, in cutoff, you can have the two levels on the two sides very different as long as they ensure that it's in reverse bias. So for example, reverse bias means the anode is less positive than the cathode, right? That's when it is reverse biased. So if the anode is at plus 5 volts, if the cathode is at plus 6 volts, it's reverse biased. But if the anode is at plus 5 and the cathode is at plus 60, it's still reverse biased. You don't care, right? It's not going to allow any current to flow through it. So just remember that rule as we look at how to solve these problems. Okay, so with that, let me open my PDF where I've solved this problem. It's actually here. And so problem 4.3 is right on page 1 at the top of this chapter 4, Diodes Class Problems. And I call this part A because these chapters are long in this textbook. I want to warn you, there's a lot of material in every chapter. It's actually, I find it much more densely packed with information than our previous textbook. So, a lot of work to do. I want to warn you about this textbook right away. So anyway, I am splitting it into two parts. Part A will have some problems, and part B, another PDF, will have another set of problems. Okay, so this diode circuit A has these two diodes D1 and D2. Which of them is on? Okay, first of all, the rules on the right side. I've got 3 rules scribbled there. I will read them so you don't get confused with my handwriting. First rule, or first condition. Both D1 and D2 cannot both be on, since voltage V cannot take two values, right? So if D1 is on, then 1 volt will come through, D2 is on, then 2 volts will come through. So this point V will have two different voltages, which is just impossible. So only one diode at a time can conduct. Now the question is, which diode is conducting? Because we need to find the current and the voltage, right? So we need to know what V is, and then we can find the current in the 2K resistor. So has the 1 volt come here or has the 2 volts come here? That's the question. Okay, so let's look at the next situation. If only D1 is on, let's see if it makes sense, or we break some rules related to diodes and electricity in general. So if D1 only is on, then D2 has to be off, right? Now let's say D1 is on and we get 1 volt here, right? D2 is really still forward biased, isn't it? Because you have the anode as 2 volts and the cathode at 1 volt positive, both are positive. And so in theory this is forward bias. Remember, for an ideal diode you just need slight positive voltage. So in theory the 2 volts is also coming here, right? So something wrong. We cannot have D1 only on, because then the conditions are not satisfied. That's how you check which of these two diodes is on. So so forget about that situation of D1 only is on. Now let's try the third possibility, D2 only is on, right? So if D2 is on, then this 2 volt comes here, right? Now what happens to D1? D1 becomes reverse biased, right? Because the cathode is at a higher positive voltage than the anode. The cathode is now at 2 volts, the anode is now at 1 volt, so this becomes off, and there is now a rule that this voltage can, has to match that anymore, because it's reverse bias. Like I just said, in reverse bias, the diode doesn't care, it stays off. So this condition D2 is possible, and so I said possible and I put a little check there, and this is how you have to check in each case, okay? So once we know D2 is on, D1 is off, then this 2 volt comes here, and now I summarize here to say V is at 2 volts, I equals this minus this divided by the 2K, and you get the current 2.5 milliamps for this, okay? Same situation for B. Again, this is a simple circuit. I know I'm probably spending more time than necessary, but you're going to run into this quite a bit. So become familiar how to analyze a circuit like this. Here we have a plus 3 volts and both of these are at plus 1 volt. And similar situation, what is V and what is I? Okay. So both D1 and D2 cannot be on, same condition as we just talked about above. Let's try to see if D1 only can be on, right? Can D1 only be on? If D1 is on, then this 1 volt becomes here, and so D2 is reverse biased, right? Because this is plus 1, anode is at plus 1, cathode is at plus 2, so the cathode is actually more positive than the anode, which means reverse bias. So this is blocked, no problem, and this 1 volt comes here, and so I put a check here to say yes, this is allowed. Try the other condition. Can D2 only be on with D1 being off? Let's try that. If D2 only is on, then the 2 volt comes here. The 2 volts makes the D1 positively forward biased, so this 1 volt and this 1 volt should be the same, right? That means this point now has a 2 volts and a 1 volt, which is impossible. So this condition D2 being on cannot exist, okay? So once you know that D1 is on, D2 is off, V becomes just 1 volt, and then if you do the I, you come up with 1 milliamp, okay? So that is the way to solve something like that. And actually the next problem is also similar, but let me go back to my PowerPoint and see what else I have. So that we did 4.3, then we looked at some rectifier applications, the logic gates, and here we are with problem 4.5, also from the back of the chapter, and it has a slight rectification battery charging situation, so let's read about it. So the circuit shown is a model for a battery charger. It's a very simple battery charger. A real battery charger is going to be slightly more sophisticated, but this is supposed to teach us about basic ideas about battery charger. So Vi is a 6 volt peak sine wave. So the charging voltage, the charging current is actually this I. Okay, I is a steady milliamp source that feeds into the battery. And remember, battery charging means you are pumping current into the battery. Just applying a voltage isn't going to do much benefit. You need to have to physically be able to send current into a battery to charge it. So the current source is actually what charges it, but this voltage source is kind of a control on it. This sine wave voltage at Vi is going to control how much charging happens. Okay, so let's read what is said on the left here. Vi is a 6 volt peak sine wave. D1 and D2 are ideal diodes. I is an ideal 60 milliamp current source, and B is a 3 volt battery that needs to be charged. So he is asking us to sketch the waveform of the battery current IB and find its peak and average values. So the battery current will not be a direct continuous 60 milliamp charging current. It will be regulated by what the sine wave is doing over here. Okay, so that is the problem, and apparently this is a model that is used quite a bit in real battery chargers. Okay, so before we go to look at the PDF and how this is solved, let's look at the notes. I'm hoping that the notes will benefit you before we go to see the problem. So what am I saying in the notes? Either of the two diodes will conduct when properly forward biased, right? When the anode is more positive than the cathode, just like we saw in the previous examples, that diode will be conducting. But also remember, it's very unlikely that both diodes will be on. Okay, only one diode works at any given time, otherwise we run into that funny situation. Okay, second note here, battery is being charged only when Vi is greater than its own natural voltage. That means the battery is at 3 volts roughly, right? Not exactly. If it's being charged, that means it's slightly lower than 3, but close to 3. And so when we know this from common sense, right? For a battery to be charged, the applied voltage has to be higher than the battery voltage. So that's all I'm saying here. And that applied voltage is being regulated by this sinus wave at Vi. Lastly, when charging, IB is fixed at 60 milliamps. So once the condition is right for charging, that 60 milliamp just goes in non-stop. Okay, so this is a simple model of a battery charger, but these 3 notes here should help you to understand the model just a little better. Okay, so I will go to my PDF, and now I'm on the top of page 2 of my PDF. So I've shown you that drawing again, and actually I redrew it slightly so that you can see that it's similar to the problem that we tackled previously in the previous example, right? This may help you a little better because the same logic we use there sort of applies here also. Okay, so either D1 is on or D2 is on, right? That's what we generally conclude for these kind of problems. So what happens if D1 is on, or when is D1 on? So D1 is on when Vi, this voltage, so Vi is here and the battery is here. This is one way to visualize it. Basically that's what is here given to us. So when Vi is less than 3 volts, remember it's a sine wave, right? So it can be like this, and I've shown the sine wave here. The peak is 6 and at some point it's below 3. Where did I get the 3? The 3 is the battery voltage. So when Vi is less than 3, current I flows through the D1 and nothing flows through the battery. So the current flows here, but nothing flows through here. So that is the condition D1 is on. And you can check this, do some math, see if, assume Vi is 2 volts and see, apply the same rules we applied to the last problem and see if it satisfies. Next, consider D2 is on. When is D2 on? When Vi is greater than 3 volts is when D2 becomes on. Now current I flows through D2 and current I is nothing but the IB, which is 60 milliamps. Okay, and these conditions you can check strictly based on the rules that I just showed you on the previous example. Okay. Now, using what we just derived here, if you look at the waveform for the battery charging current, this is what it looks like. And this is what we've been asked to actually do. Draw the waveform and then find the maximum value and the average value. So while the applied control voltage is a sine wave, the actual battery current is more of a pulse. Okay? And so the battery current flows between theta and pi minus theta, assuming theta is where you hit that 3 volts limit on the AC waveform. Okay? So I'll show you how we get that 30, but let's assume theta is the unknown now. But we know that just based on the symmetry and the way the graph is, that the waveform for the current is on at this point, theta, and turns off at pi minus theta, because 2 pi is 1/2 cycle. Remember? Yeah, 2 pi f is omega, so 2 pi is 1/2 cycle. So this is pi minus theta point. Okay? Alright. So how do we get that theta? Here's the derivation. So we know that the voltage in a sine wave is Vmax sine something. And we know that the peak voltage 6 happens when sine 90 at sine 90, when this alpha is 90. So 6 equals 6 sine 90, 3 equals 6 sine some theta, and theta is what we want to find. So if you take the ratio of sine theta by sine 90, you can find theta to be 30 degrees. So the average value of IB is the amount of time it's been on divided by the total time it could have been on. So it's only on for 120 degrees. So 60 milliamps on for a third of what it could have been on gives you the average value of 20 milliamps, and the peak value is 60 milliamps. Okay? So that's how you solve that problem. Okay? I'm going to move on. I think I have one or two more problems. Let's see, I know we are running short of time. So I have a problem on slide 13 and I have a problem on slide 14, and we should be done with this section. So let's quickly look at problem 13 and problem 14. Hopefully they're not very difficult. So problem 419 says on slide 13, a diode for which the forward voltage drop is 0.7 volts at 1 milliamp is now being operated at 0.5, and what's the value of the current? So to get 1 milliamp, the drop has to be 0.7, or for a drop of 0.7 we have 1 milliamp. For a drop of 0.5, what's the corresponding milliamp? Pretty simple. Let's look at the solution. 417. Oops, sorry. Yeah, 419 is what we are looking at. I'm on top of page 3. IS is not given, right? If we had IS, we don't need all this jugglery. So we have to pretend like we don't know what IS is. We don't even want to take a guess. So we have one equation for I. We know how to write that. We use Vt, which is roughly 25 millivolts. So we write two equations, I2 and I1. I1, we use the 0.7 volts, and that results in 1 milliamp, we know. I2 we only know the 0.5 volts, but we don't know I2. So you can write a ratio, and if you simplify that ratio, you come up with this value for I2 should be this. So I don't have much time to spend on this, but please take a minute to familiarize yourself, because this concept of taking that ratio I2 by I1 is important, and we will use it a few more times. Okay. All right. So I will reduce this. Go to, sorry. Okay. Next question. Next problem is problem 426. Slightly more complex. So let's spend a few minutes on this. For the circuit shown, and I'm on slide 14, both diodes are identical. Find the value of R for which V equals 50 millivolts. So we have a current being given. We know the two diodes. There is a resistance in the circuit, and we need to find out what the value of the resistance is when V becomes 50 millivolts. So V is given. We know this I is given, the diodes are identical, but we don't know if they are, ideal. So we have to assume they are not ideal, and then we have to solve the problem. So what are the notes before we start solving? By KVL, we can say that D2, the voltage across this diode is the voltage across this diode plus that V. Okay, if you think of this as a loop, then VD2 equals VD1 plus V. The current ID1, which is this current, will be V by R, right? If the current is all flowing here, then the current will be this voltage divided by this resistance, right? That is the current flowing in this diode, because it's in series also. Also, ID1 plus ID2, this current and this current will equals 10 milliamps, the source current. Okay, so with those notes, let me go to show how I solve V26 or problem 26. So we know V2 is 25 millivolts. We are writing again two currents, right? Because we need to find, what are we asked to find? Find the resistance, right? And to be able to find the resistance, we want to use that equation we just came up with, that the current here equals V divided by I, right? Resistance equals V by I or current equals V by R. Either way, you can use that equation to solve. So I'm writing two equations, one for diode 2 and one for diode 1, and then there is a ratio that we just saw previously. Okay, here V is D2 minus D1, VD2 minus VD1 because of the KVL. Also, the ratio of I2T by ID1 is this, right, based on the previous rule that I showed you. And so we have to find R for V equals 50 millivolts. That's the goal. So in this ratio, if you substitute the known terms, right, we know V has been given and we know Vt. So this is a known quantity, 7.39. This is this ratio also, right? This equals this. So this ratio ID1 by ID2 is this value, and we know that the current I is given, the total current, which is 10 milliamps or 0.01 amps, and then we know the voltage, which is again 50 millivolts, 0.05 volts, divided by R, and the denominator is again V by R. Okay, and this ratio, be careful how you derived it. Okay, we derived it using the previous relationship that I had here. Okay, ID1 and ID2, right? So using this relationship, we set up this equation, and so we have all the values we need except for R, and then if you solve for R, it comes out to be about 42 ohms. Okay, So take a minute to familiarize the ideas behind this problem, and if you have a hard time understanding, let me know. Okay, so I'm going to stop this and we will continue with a lecture recording in my next recording.